All right, so this is a bit different and cool. We're reviewing a YouTube video from a Grasslands Conference. Tell me about that.
Yeah, no, it's something I picked up the other day, and I thought, shit, they've got most of the points in regards to carbon in the soil. And there's various questions that are asked. And it was a really good process that Louis Schipper from Waikato University put together regarding the carbon stores in the soil and what they understood.
Yeah, he's got a really good understanding of it, doesn't he?
Yeah, and I just thought we should just have a few comments, and this is a good way of actually explaining to people without going all the way back again and starting all from scratch. And this guy knows what he's on about, and it's worth commenting.
Cool. Okay, well, let's bring it up on YouTube. Okay, here we go, and we'll comment on this as we go.
Yeah, no, and there's some really valid points, and it's just we've put some stuff to go alongside it, and some numbers from what we've seen happen, and certainly comment on some of the things that he talked about that they didn't know why this wasn't responding, and we certainly have a fairly good understanding now. So, let's roll on and see how we go.
So, thank you very much, Warwick. Apparently there are a few questions out there for me. And others, so maybe that'll happen a bit later on. I'm going to present on behalf of Aaron Wall and Jordan Goodrich, who are my co-authors. Aaron just finished a PhD, and a lot of this material in here is from that. I want to start by pointing out, and I think we know this, New Zealand carbon stocks are quite high relative to the rest of the world, so about 30% more. And it is spatially distributed, so we have quite a lot of carbon in our soils. And we've just heard about why carbon is important in terms of sustaining soil quality and providing nitrogen and phosphorus and a lot of other properties as well for supporting resilient pastures. There's also the fact that our terrestrial ecosystems, the soils and the plants, have taken up roughly 30% of the fossil fuels that have CO2s that have been emitted into the atmosphere. It's been doing us a service. How long this will sustain, we don't know, but there are two very good reasons for maintaining carbon contents in soil. My job is more to talk about what kind of aspects around resilient pastures we need to maintain or increase this carbon stock. So like Mark, I think simply about soil carbon and its stocks. We've got a plant on the left-hand side there that's dropping leaf litter and root litter. That gets fragmented, and that forms what was referred to before as particulate organic matter. That's organic matter that if you got a microscope out, you could identify it if you knew what you're doing, a root or a little bit of leaf or something like that. And then we had a little bit of talk about what the microbes are doing. What they are doing then is processing that material. Some of it spills out, some of the microbes die, and that gets what I think of welded onto clay and mineral surfaces where it is protected. That's called mineral-associated organic matter. And that's the material that we want to have if we want to sustain our carbon stocks in soil, because it's highly protected and it's not going anywhere. So how do we manage this kind of a process so that we keep carbon in our soil and we get these wonderful functions that Mark was talking about, and the carbon sequestration as well. Now, one of the important aspects that come out of this then is that a lot of the carbon that is in soil comes from roots. So what you see above ground isn't necessarily helping you as much as you might like to think. It's coming mainly from the roots because of this processing through into the mineral surfaces.
Okay, let's stop there for a second. He's talking all about carbon and in the soil and everything, and people don't like he's spoken about other presentations at the conference and that. And basically I just thought, well, let's bring a little bit of science or a little bit of reality of what happens when the carbon comes into the soil. So if we go and look at our presentation to go with this, okay, just give it some background, some scientific background and some numbers, because people don't realize how big this numbers game is actually. Okay, so in this regard here, organic matter changes, okay? So we've got to notice the difference just between organic carbon increase. So 1% organic carbon is equivalent to 2% organic matter.
That's something to get your head around to kick off with, actually.
And look over to the right-hand side of the screen. It says humus contains 50 to 60% carbon. See, so like this is double the number. So you get organic carbon in the soil, and you just double it up and you get the amount of humus in the soil.
Okay.
Okay. Now, when he talked about organic particulate sticking to the soil, I talk about humus. And it really has to be digested completely to actually stick to the soil and do its job. And just look at the numbers. I mean, there's 30 to 40% carbon, 3 to 4% hydrogen, 4 to 5% nitrogen. This is a biggie. It's a real biggie about this.
This is where we start getting into, when you realize this, there's less need to put nitrogen on.
Absolutely. Like when you start bouncing the numbers up and you start realizing, look at the phosphorus at 0.4 to 0.08 and going, these are numbers are pretty big too. Sulfur 0.4 to 0.06. These are big numbers when you start to actually calculate right through the soil. They're huge numbers. But this is basically all humus, when it's digested, fits within these ratios. And that's not just dead organic matter on the soil. It's broken down, digested, and it's holding onto the soil. It's got a job. So we move to the next screen. So you think about this. So in a soil test, we always test the top 150 mils. Okay,
Yeah.
so in a hectare, that's 10,000 square metres, 100 metres by 100 metres, there's 1,500 cubic metres, or if it was at 1 tonne, 1,500 tonnes of soil in per hectare that we're dealing with. So if you increase the organic matter by 1%,
Just 1%.
just 1%, there's 15 tonnes increase.
Holy heck, that's amazing.
1% organic matter increase, you've lifted your soil weight by 15 tonnes.
Yeah.
Now, to go with that, look at that. When you calculate the numbers, you've just put 675 kilograms of nitrogen. That's about 1.3 tonnes of urea.
Amazing.
Yeah, and so it doesn't have to go much, and there's some massive changes happen. So 7.5 kilograms of phosphorus. Now, this is really important because, like, if you look at a dairy farmer who's doing 1,000 kilograms of milk solids, you take off the farm about 0.6 or 6 kilograms per 1,000 kilograms of milk solids per hectare.
Yeah.
We've already got it covered.
Okay, but it must be that's oh my God. I mean, it's expensive stuff if you're going to put that on, right?
Yeah.
So how difficult or expensive is it to get that just 1% increase?
It's not hard at all.
Okay.
It's not hard at all, but you just need to know the limiting factors. And as we go through this video, and Louis Schipper is going through and he's showing the different things that are happening, I go, I know what causes that issue. And we can actually talk about it and see, look at the amount of sulfur. And like, these are the things that we see when the soils become really healthy. The sulfur availability comes up, the nitrogen availability comes up, phosphorus is hanging out there all ready to go, and we don't see it escaping into the water. We see it in a really healthy way. It's like, this is food for the plants, but it ain't going out in the water because it's bound into the humus part of the soil. It's brilliant. You know, nature's a brilliant beastie thing.
Okay.
So if you look at it, yeah, just put it into the next context, just to give you a context of this.
Do you want to see the next slide?
Yeah, we'll have a look at the next slide.
Sure.
So now, this is the difference between a soil that has got 8% organic matter and how much nutrients available, and 16% organic matter.
We've had actually a bit of a jump here from 1% and 2%, though.
Yeah, I'm saying every time that 1% goes. But like when we go and do soil samples, right? This is why I've put this here. We regularly get samples over on the left that are 8% organic matter.
Okay. So the 8% sort of represents something that's kind of average?
Yes, we see that a lot. It depends on the soil type and who's farming it, whatever, but we see that a lot.
But to double it's got to be...
No, this is where we're at.
Really?
This is where we're at.
Wow.
So if you look at it, now I've got 10 tonnes of nitrogen per hectare, which is 20 tonnes of urea. I've got double the amount of phosphate available through the humus.
Those numbers are huge.
Yeah, the bounce.
10,800 kilograms?
Yes.
Of nitrogen.
Yes. Now, and you've seen this picture of the farm, and we've done the water tests, which we're going to talk about in another video, but like my water test showed 0.07 parts per million of nitrate nitrogen leaving the farm.
Right, so you've got it in a form that's really locked into the organic matter.
It's in the soil. So what happens with organic matter, when it oxidizes, when it gets hot over summer, it oxidizes off and releases the minerals. The carbon dioxide then becomes available for the plant because it's got to photosynthesize, it's got to take carbon dioxide in, and then the minerals become available in the soil. Nature's got a far sorted out way better than we do.
Without spoiling what's coming up, but I've watched the video ahead of time, there's a moment where Louis talks about we get to the height of summer and then it starts to drop, right? Now, I know what's coming, but you just spoke about the heat of summer making it come out.
Yes.
So that becomes a problem in his graph. He's got good information too, doesn't he?
Yeah, no, great information. But
he highlights that. We'll see it. He highlights that as an issue.
Yeah, and I see that what we've missed, and we'll talk about this again, the things that we've missed in organic matter production and have not been talked about, but he shows you where they start going wrong. And we'll just keep going, Stephen, because otherwise we'll be here all day thinking about what's going on in the future. But look at the numbers. They're massive.
Yeah.
You cannot afford to put these sorts of numbers together all the time by paying for it out of a bag.
No. And
it won't hold. The more that you try and put the one on the right hand in place, the more it goes down the drain and the less you get on the left-hand side. So it's a disaster waiting. You keep throwing it at it, it won't work. If you nurture it, it'll work for you.
Okay, we'll head back to the YouTube, eh?
Okay.
About resilient pastures and how they may contribute to maintaining at best, at worst, or improving the carbon stocks of soils. What do we need to be thinking about? And just as a quick aside, the majority of New Zealand's soils are at steady state under flat land for carbon contents. We're not quite sure what's going on in the hill country. We're working on that. That's something we can come to. The reason that we have carbon in soil is because we have a small difference between the amount of photosynthesis that we have coming into the system and the amount that's going out in respiration. These are two very large processes that are going on every year. And as that carbon goes into the soil, it gets stabilized by microorganisms into this particular organic matter and the mineral-associated organic matter. And we want to get it there so that we can hold it, in this case, for the services we were looking for. So these are my key messages that I'll come back to. And if we're thinking about resilient pastures, this is what we want to try and do. Maintain cover. Continuous inputs of carbon into soil, which may mean that we need pastures that require less renewal. We may need to think about optimizing the supplemental feeds that we use because they go through renewal periods as well, and I'll show you a little bit of that in a bit. One of the key things, and we've heard this multiple times, what is the roles of roots? We need to maintain roots and root inputs into soil, and we need to make sure that we are getting dung returns back to the paddocks, and we'll talk about that in a bit.
Okay, now we'll just stop there for a second. So this is really interesting. You know, we're talking about photosynthesis or against respiration, right?
Yeah.
And we're caught in this visible world. We're caught by the plants that are growing, and Louis is going to talk about these other plants and their roots and all that. And yeah, I hear this all of the time. You know, like, Christine Jones is the liquid carbon pathway, the stuff that comes down the plant and into the roots, and this is the process that it goes about. And I'm going to challenge all of that because what we've seen is that people have neglected the single basis of the whole of humanity, which is a cyanobacteria, which is actually the part that does the job.
Mm.
And I think it's something like 85 or 90% more efficient at photosynthesis than any other plant on the planet.
Yeah.
Now,
it's a bacteria.
Well, it's a plant, but it's an interesting thing. It's a photosynthesizing bacteria.
Okay.
It's got all the organs and every part of it, just the same as all the cells that are made up in our bodies.
Mm.
And we're going to do a video or two or three on these little critters as we go forward because they're seriously important. They have DNA and they have all the cell structure. They have every function about waste and we'll be able to watch how little grubs come along and gobble them up just like cows eat grass and all that sort of stuff. But we can't see it.
Yeah, yeah.
We can't see it, so it doesn't exist. But you look into cyanobacteria and you see that the world changed when cyanobacteria became part of the environment because it went from a anaerobic situation to an aerobic all of a sudden. So then things can function, can respire with us. And what happens with that is that if it's going through photosynthesis, it takes in CO2 and it kicks out oxygen. So where did the carbon go?
Yeah.
And, it goes in the soil. It's like, dear. We see it by our observable nature in the wintertime when they go nuts because they love living in a moist situation.
Mm.
They don't mind, they like it warm too, but most of the time you can't hold enough moisture in the soil for long periods of time over the summer for them to produce. So it's the wintertime that they actually do all the work. But, this is where I'm going to challenge what we're going to hear from Louis Schipper next. But this is cool material about how he's saying how the carbon stocks hold in the soil and what they do and respiration, all that. But I would like to turn that graph upside down.
Right.
Okay. I'd really like, and we'll go on a little bit further on this process, but it's a cool bit of science. And I mean, these red lines, as he'll talk about, are different, and he's got some other graphs. So they've done some really cool work.
Yeah.
But what I'm taking is the practical side of thing of being on the farm, observe what we've done, seen the limiting factors, and know how to fill these gaps up and take advantage of that situation.
Okay, so what have I got here? This is some data that we've been collecting over the last 10 years or so. It represents about 25 years of CO2 exchange data from paddocks. So this is pasture scale, half-hour measurements of CO2 exchange, and the paddocks there are those grey lines, and the average is in that black line there. So you can see that you get a little bit of a gain in summer there, and then as you go into autumn and winter, and then into spring, autumn and winter, you're losing carbon, and then into spring, you're getting this carbon dioxide being recovered again. Now, it looks like the system is gaining carbon, but you now need to subtract off what went out the gate in milk, and you need to subtract off what came out of the cows as CO2. And then you find that these systems tend to be pretty much carbon neutral. The point here is that the three red lines are three paddocks where they've gone through pasture renewal. So there was a time period when those soils were bare, photosynthesis stopped, so your carbon input stopped, but the microorganisms, they keep churning away and you lose carbon. So you come to the end of this year for those renewed pastures and you've lost carbon. How fast they recover, we don't really know that very well yet. Probably is going to happen, but we don't really know all that well. So if we can reduce the number of times that we do this, that would be great.
Okay, right.
And you agree with him on that, don't
look,
you?
I totally agree with him, absolutely. But let's just back up just a fraction on the video there, Stephen. I totally agree with him on this. And he says he doesn't know why. And this is where this part of my dislike for chemical farming.
Sure.
Because what's happened here is that with all, or 90%, and I can't be guaranteed that this is done this way, but Pasture Renewal comes in with a chemical spray. Okay, and one thing I know about cyanobacteria, there's two things they hate.
Yeah.
There's chemicals and aluminium. They despise both of them. They can't handle either of them. And so what we've seen in these red lines, what he's got here, is there's no cyanobacteria to bring this back. And it's got worse in the middle of winter. Okay, see how it's dropped right down in the middle of winter?
Yeah.
Okay, and that's when they should be going balonkers.
Yeah, and because you said in previous videos, they're found even in some of the coldest climates on Earth.
They are the most robust environmental biology on the planet. They can live in the Arctic and Antarctic. They get frozen to minus 40. They come out swinging in the spring. You get some electricity, you get the water, salt water dilution, bang, it takes off. Next thing, the krill eat them, then we got the herrings, and then every part of the whole food chain relies off them.
Okay, but they still so my point about them being found in cold climates is we shouldn't necessarily see things die off in winter, but you've said that they do come out swinging in spring, so they prefer warmth.
They can, but that's down there because they can't move in the frozen. Okay,
sure.
Okay, but in our situation, if there's moisture in the wintertime, they can function. They can photosynthesize because they're not temperature reliant.
Well, we certainly have moisture in this country in winter.
Absolutely. And this is what we've seen is you can see the explosion on the farm by the worm castings that come up after the right circumstances. And I mean, we get 15 mils of worm castings when these guys go off. They photosynthesize the right temperature, right moisture, worms go mad. They bring all that nutrient back to the surface again. So these guys are photosynthesizers, bringing up the phosphorus, bringing up the sulfur, bringing up the nitrogen, getting all the minerals in order, and you bring it back to the surface, ready for spring. And so this is where I'm saying, I know exactly what happened there. They would have used a chemical, and they would have knocked out the grass that they had at the time, and they knocked out the cyanobacteria, and he's hoping it will come right. It's not the roots that are putting the carbon in the ground. It's the cyanobacteria. And the more that you get them in a healthy state, the more grass you grow, the more carbon you grow, the more everything you grow.
Mm.
And so what we're seeing is a distinct process of what happens when you use this. And they've done the modeling and they've done the testing. I mean, we test the outcome with the soils. These guys were testing above ground biomass, CO2 emissions. They were testing all of those things and putting it into one process. So that's cool. I'm really pleased. They've done a fantastic job.
Yeah, and would you have been able to have figured out that the spraying was happening here if they hadn't essentially spoken to it?
Well, it just showed. They said, well, this is what we've done, and I wouldn't have known there was any variance between the different aspects of the different soils they've tested, but they just said, well, these were regrassed, and it's like, bang, well, we're going to see a little bit more of that very shortly.
Okay.
All that well. So if we can reduce the number of times that we do this, that would be great. I want to now look at supplemental feed. In this case, I'm looking at maize silage. I'm not picking on it, but this is one that we've got some data on. About 5 years worth of data there, the green line there. Now we're talking about total carbon balances for the system. So that includes everything, milk and cow respiration and all the rest of it. And you can see with that green line, it's basically hovering around zero, little gains, little losses, little gains, but in a really reasonably predictable way. Now, if we take a paddock close by and we run this through maize, this is what we observed over that time period. So you can see 2 maize periods there. There's a lot of ups and downs in there that I can explain, but I'll leave for the present. The big one are these very large losses that you can see towards the end of the season as you basically come and take all of the above ground biomass and put it somewhere else. So these systems lose large amounts of carbon. I think, nearly 15 tonnes of carbon over that time period. It's gone back into grass now, and the thing that we were hoping for was to see some sort of recovery start, and we have not observed that yet, so that carbon would accumulate again back into those carbon pools. But we're yet to see that. We hope to see that in the future. But
Stop there. Yeah, and this is we hope. We hope.
Yeah.
Okay, and this is where the hope has been beaten to shreds by the chemical inputs of the maize cropping.
Mm.
And so what's happened is that it's cool. This first time, this is where if you use the visible aspect all the time, you wipe the paddock out with a chemical, you plough it or whatever else, and the maize grows really high. Okay, the microbes have died. The carbon in the soil oxidizes, which releases CO2 for the plant to grow. It releases the nitrogen from the organic matter that's in there, and it releases nutrients. So you grow a great, really good crop, okay? So let's have another go. So I'd say they would have struggled the second year, in year 2018, 17, 18. They would have struggled to do a crop as good as they did the first year because the carbon's dropping and the available nitrogen's dropping. But again, the same thing.
Is that because it's depleted from the first round?
Yes.
Yeah, okay.
And so it's doing it again. It's oxidizing the carbon. It releases the CO2 so the maize can grow. It releases nutrient. But then we end up with a paddock with 16 tonnes less carbon. Okay, so then if you look at those figures that we were at the start, now we've lost a whole lot of nitrogen, like we've lost a whole lot of phosphorus, we've lost a whole lot of sulfur. Okay, and so when we look at this, 2018, 19, 19, 20, okay, 3 years later, it's
still really, really low.
It wouldn't recover.
Yeah.
And we know how to get those paddocks to go again. But you've got to get the biology in, you've got to get the limiting factors fixed up. And this is the part where, have a look at our soil test video. That's just part of the limiting factors. But, when we look at all of these processes that we put in place, the amount of dry matter you got to grow on the top of the ground to what you lost underneath the ground, what benefit was there? You went to a lot of work and to actually lose what was underneath the ground. And this is the part about doing soil tests, GPSing it, actually getting all that data all the time. It's not as it's not so comprehensive of what they've done in the testing, but it really shows. Here's a result. My organic matter's gone up 1%, therefore I've gone up this amount, or it's gone down. So therefore, what have I done wrong that allowed it to decrease? So these are the things that we do know that we can affect. And we'll see that as we go further forward. But this was a prime example it's not the roots. It's the cyanobacteria and the biology interfacing to create the humus that builds the organic matter in the soil. Long-term sustainability. The chemicals, the aluminium that come in this sort of process, poof, gone. See you later. I'm out of here. So you've actually done a major disservice. When we grew maize on the peat, the whole process was out trying to make the soil nicer. We weren't trying to grow a maize crop to just get the dry matter. We were trying to grow maize, but look after the soil so that when we got it back into grass, it actually grew way, way better than it ever did before.
This might seem a bit naive, but is there a way of growing maize that improves the soil?
Absolutely.
Like it's a particular technique to it?
Yeah, it's all about preparation.
Okay.
The whole thing's preparation. It's all about knowing well out in advance that I'm going to do that paddock and maize. Okay, well, you've got to get your systems in place and you've got to get your available nitrogen and when the way that you cultivate and you don't use the chemicals and you take the maize off and then bang, you in getting some cover over the ground. Maize does a pretty good job of covering the soil when it gets up,
Right.
It doesn't take very long. So you've just got to take a completely different approach to it.
Well, that sort of reminds me of the most previous video I think that's been out, which is the coverage of weeds being helpful.
Yes.
But maize is sort of performing a function there where coverage assists because it prevents the respiration of the land.
Yes, it does. And that's the key thing about this process. Because
sort of evaporation, eh?
Yeah, evaporation of carbon out of the soil.
Yeah, that's what I'm getting at.
Yeah. And so the thing about maize crops and everything, when you set it up properly, and as I spoke about in the weeds, is that when you get a good decomposition of carbon, the carbon-loving plants or the plants that turn up to actually give you the carbon back, they don't know it doesn't need to be there. There's no point. It's all right. It's okay.
Yeah.
Okay. And so the maize goes in the ground, and once it gets to this high, and if there's no problem, well, you've covered the weeds. They're not a problem again. They're gone out the gate. So it's preparation. And I'm talking with clients down south now who are putting their winter crops in end of November, which is right now, and I'm saying, have you picked out what you're going to do next year? And go, why? And I go, if you want the best crop that you can ever grow at the healthiest thing, you've done this one this year, but where's your cropping ground for next year? We need to set that up. Now, we need to be starting to work ahead of time to build the carbon level up in the soil and build all these other parts so that when you cultivate it, we don't have the issue of weed infestation coming in. We've had your nitrogens all ready to go. Everything's, look at the number. Put it up 1% organic matter in the 12 months before next year's crop, and you've got all the nutrients you need.
Okay, are you saying in that scenario that you would ask those farmers to rotationally move where it's going to be grown?
Yeah.
Or is it a case of it can be grown in the same place, but you've got to do some things?
Yeah, like with these guys that are doing these winter crops in Southland and that sort of thing, 1 or 2 years. But if you're going to do it really nicely, set it up. But even then, set it up a year in advance. But you want your soils better at the end of it, not worse.
No.
And these guys are ending up with it worse. And I'm going, no. Take the opportunity to make it better.
And so if I could be so bold as to say if they're going in a scenario where it's getting worse, they're following exactly this situation on the board here.
Yeah, that's right.
In this video. Okay, do you want to carry on with where he's at here?
Yeah, no, I mean, thanks very much for doing the work and showing us the exact figures. This is what we see in our testing all the time. He's put it together. I mean, I haven't got the funding that these guys have got to go and do this work, but I'd dearly love to, but yeah.
Yeah, sure, okay.
Wait and see. One of the other problems or interesting things that happens with particularly this, with maize, but possibly other supplemental feeds, is they look great, right? Because you get, this is the CO2 uptake by pastures and maize for those two sites, 18 tonnes and 20 tonnes. And where does all that CO2 go? Well, a lot of it goes straight back into the atmosphere through plant respiration as the plants grow, but not as much in maize. So maize is not putting so much back into the atmosphere. And that is why you are getting these really large amounts of biomass, above ground biomass in the maize relative to the pasture, right? Because it's not respiring as much. The kicker, though, is that the pasture is putting more below ground into the roots than the maize is. And so now you've got less carbon that can now feed into the soil carbon and be stabilised. So here's a challenge for us, right? How do we keep our carbon stocks high by maintaining root inputs into the soil so that we can sustain our carbon?
That's the point we noted earlier. How do you keep carbon stocks high? By maintaining root inputs into the soil so that we can sustain our carbon. Is that something you wanted to speak to?
Yeah, well, I think this is where, I can just bring up our graphs about what we've done and just show people a little bit of an inclination of like, this is these sort of are representative of what happens on farms when we're working on them. And it doesn't happen every time straight away, but in most of the time it does. But if we've missed something, limiting factor, it's a good indicator that we've actually missed something and we've got to go back and have a look at it again. But if we have a look at it, it just shows you that we do know how to hold it and to increase it and let it do its seasonal thing and to actually work for us. So these are some soil tests we've done at home. And just to give you an idea, they were a year apart and a few years back now, and the carbon price is certainly a lot higher than it is now. Back then it's only $25. I don't know what they're running at the moment, but just to give you an idea, and they've got the GPS coordinates starting and all that, but in the top 150 millimetres at the time, our starting point, we had 7.85% organic carbon.
Right.
Okay, so you got to measure the organic carbon. Otherwise you end up with limestone and all these other things. It has to be organic carbon. So, and down here, this is our bulk density, and we're on a light soil. So it means it's per 100 millimetres, like a litre, it's only 620 grams of soil in it. So the following year, and we did the test again. We're doing this regularly, like 18th to the 10th, 27th and 9th. We're trying to do it within a month, just depending on weather. We went to organic carbon in the soil to 8.95%. So we increased it 1.1%. Okay, so then we went up a whole 1%, which is...
Well, this is matching the figures you gave before in a way, because you've gone up just that 1% from 1 to 2.
Well, actually, it's doubled it.
Yeah, okay, true.
Okay, because the organic carbon...
Of course, it's double. Yeah.
It's doubled it. So we've gone up... we got 2% organic matter, okay, in that time. And so then if we look at the bottom 150 as well, and we started at 3.94% organic carbon at 0.75, and in that time we went to 4.38, and the bulk density dropped just a fraction. But, like these numbers are huge when you talk about the increase in tonnes. Now, there's a calculatable figure just straight underneath this, is that you take the number of the carbon, the actual carbon, and you times it by 3.67 to get the tonnes of CO2 units. Right. So down the units here on the bottom one went from 44 to 48 tonnes. And so that's I think, like equivalent today about $320 a hectare in the bottom if you were selling the carbon credits. And we went from 73 to 87. So we had another 14 tonnes of carbon and of CO2 units. So like in total, we had 20 odd tonnes of carbon CO2 units that we could sell.
Yeah.
These numbers are not insignificant by any stretch of imagination, and this is what we see all the time. But this is what about is soil health. And I've been told, you're not a bee farmer, you're a cyanobacteria farmer. And I go, that I am.
Yeah.
We just conversion. We're in the total conversion. And when we talk about the cyanobacteria and we do the video about it, I mean, they change the planet.
Yeah.
They change the planet every year. If we didn't have cyanobacteria, we wouldn't be here. There's nothing to talk about. There's more transpiration than all the Brazilian rainforests and everything by multiple times in the ocean using cyanobacteria. And this is the thing. They don't mind living in the water. They don't mind living in soil. They actually love living in soil as long as there's no chemicals there and there's no aluminium that go with them. Right. And this is what they can do.
Okay. With that shift in carbon, maybe it's a topic for another podcast, but are people actually selling their carbon?
Well, there's the people out there in the voluntary market. I just haven't been. I've nudged into it and looked at it.
Yeah.
And just there's so many other things that we got to get done. Maybe if somebody wants to come and buy it off us. But, when we do the soil test, we actually map the farms. We can actually calculate how much it is. And this is what we've done with this calculator.
Well, how would that work? You prove that you've attained a certain amount of carbon. Then someone buys it off you in the form of purchasing carbon credits on some registry. But then what if you lose that carbon later? How does that work?
Well, that's the big thing that everyone's been worried about. Oh, if I put it in there, what if I lose it? Do I have to pay the money back? And if the carbon's gone up in price, am I going to lose money? And and so there's a little bit of, I know. And which just seems quite bizarre because, you can grow a pine forest. And they just calculate on how much carbon they think is going out there. They don't even do any soil tests underneath the soil. And we know that under pine forest, the carbon crashes unbelievably so because there's no cyanobacteria or anything to function there because all the pine resin and everything else kills it all. It's a bloody bonkers system, but they just hand out the money. But this is an interesting scenario of what happens is that you can actually build fertility, build carbon. If anything, it's a great way to put a defensive system up against the councils and everyone else. It's like, excuse me, I've gone up. You owe me.
Right.
So, and additionally with the maize, we're now harvesting that material. So we've done, this is conceptual, right? A diagram of the sorts of things that we're sort of thinking about here. So we've got time along the x-axis there and soil carbon stock along the top, along the y-axis there. And if you look at that, the very top line there with the dashed lines, that's if you go through a pasture renewal every 7 years, every 7 years, 10 years, and you have enough time for it to be able to recover back to its carbon stock, and then it drops off and then goes back up again. But if you now drop that to going every 7 years renewal, then you start to get losses over the long time as it grades down, and then the dotted line there is what might happen under maize. Now, the difficulty in doing something conceptually like this is that we really need much better data on the recovery rates of that carbon stock and soil, and we don't have much in the way of measurement in New Zealand. I'm sure there are models that can address this sort of thing, but we really need hardcore data to be certain. So,
yeah, and you've been doing that. You've been doing that, haven't you? And you've got hardcore data in some respects.
Oh, absolutely. This is the part that there are certain protocols. There's, Western Australia's got a protocol. There's various around the world. Even a lot of people might have seen the Carbon Cowboy stuff on YouTube and that. There's a guy called Rick Teague, one of the professors at Texas A&M. His data protocol's very, very similar to ours. Is like they say randomized, and so when you're doing it, you don't let a computer be the random, because when you walk out in a paddock, you've got to take into account troughs and all the other sort of bits and pieces. But once you've got the set the first time and you just go back and do it again, the accuracy of being within this amount of space, getting that data. And yes, and we are accumulating that data according to their farms and how they're going. And it's phenomenal, the changes that are happening and what comes out from the testing and how the other numbers start playing up. And as I say, really good to have a look at the soil test video that goes with this.
Yeah.
It's critical. And so from our perspective, what they've done here is looking at the carbon, but we've been looking at all of these facets because we're farmers. And we I like being lazy. And when they talk about pastoral renewal and all this sort of stuff, well, they're talking 7 and 10 years. And I think 120 is about, or 100 might be about where we're at now from when we've never regrassed anything. Well, I tell a lie. We contoured the runway and put it back in grass.
Right.
Yeah, but the interesting thing about it, it got taken over by all the grasses that were all around it. So all the red clovers have come in and all the natural plantains and everything else. It's like we are not short of species, but the species will only arise when you actually suit the soil fertility to match them, not the other way around.
Hang on, I got to ask, does that get in the way of runway activity?
Terribly. Yeah,
gross. So what do you do then when you've got an airplane landing on your own ground, which you've contoured with a specific grass, and then all the old ones came back?
Yeah, they grow too fast. There's not enough days.
So what do you do? Do you mow them?
Well, I haven't as yet, but I think I might have to.
Yeah.
The cows are on it far too much now because they've got too much grass on it.
Right.
Yeah. So no, it's an interesting process. When we went through 5 years ago, when we were all in lockdown, and we had a whole lot of pine trees went out, and so when we cleaned up the piles and burnt everything and regrassed it and everything, I got some of these fancy species and all these different things that they're talking about that they regenerative and want to do this, and they grow X amount of tons of dry matter, and I'm going, well, I'm going to give it a go. I'm going to give it a go. So we put these flash species in, and the first year, I must admit, they were pretty freaking impressive.
Really?
Yeah. The second year, they were just ho-hum, and the grasses, our grasses just took over again, and they're gone.
What on earth? What on earth leads them to sort of be flash in the first year or so, and then they just don't hold?
They're built to a soil suitability sort of thing, and there's no competition when you put them on. First off, they just germinate because the ground's open, bare, put the seed in, it grows, looks fantastic, but they don't last. And all our own species just move straight back in, and you just wouldn't even know where you'd been there.
Good model if you're selling it.
Yeah.
Because just...
it looks fantastic, but it doesn't last. So what we've seen...
Well, you got to keep buying it.
Yeah, I don't like that idea.
No.
I said I was lazy as well as didn't like spending money.
Lazy and Scottish.
Yeah. That's right. Yeah, so when they're talking about these pasture like all of these things that they're talking about are bringing the carbon levels back up, I'm going, nah, we can get them up. And what happens is when you get them up to, in our lighter soils, when you get them up around 8-9%, all of a sudden the soil starts getting deeper.
Right.
It just goes south. And so the amount of topsoil is a reflective to how much grass you grow. So the more topsoil you've got, the more grass you grow. And we're just seeing this more and more. And some of the things that we've seen is like, oh my good God, this is going to be outrageous next year. It's been pretty outrageous this year, but I can see, we can go again. It's going to go again. But it's not a case of throwing products at it to make that. The product doesn't grow the grass. The product creates an environment for cyanobacteria to do their work, to then let the grass grow.
Oh, that's a paradigm shift, isn't it?
It is a huge paradigm shift.
Yeah.
And so this is why we're so hot on getting stuff done in the autumn and dry climates. In the summertime, like I got no problems working down. Anyone that's got irrigation, you can go for it anytime because as soon as the moisture's on there in the warm climate, you can actually get it to go. So it's cool. But, like if you've got a dry spell in summer, it'll slow down or stall. But anyway, I mean, when you can get the stuff on, you can get it on and get into it.
Yeah. Okay, well, let's head back to finish up the end of this little video.
We need to understand that a little bit better. So just to come back to the conclusions then, if we're wanting to maintain carbon in soil and we're thinking about what do we need out of whatever we consider resilient pastures, which is beyond production but environmental benefits as well, it's about maintaining cover in the soil so there is continuous carbon inputs into it, and that it is particularly important that we think about the inputs into roots, not just what we see above ground, so that we maintain that carbon stock. If we harvest all the above ground material and we take it somewhere else and we're not having the animals eat it on site, we are going to lose the dung inputs into the soil, which also carries carbon with it and sustains carbon stocks as well. A small amount, but an important amount. So with that, I'd like to thank the ability to be able to speak here and the sponsors for my work, New Zealand Agricultural Greenhouse Gas Research Centre, and kia ora. Thank you.
So we're going to back up a little bit to the last graph on this one.
Just there.
Yeah, no. So in total, just a great presentation, a combination of a huge amount of research to a very small process. I mean, there'll be a screeds and screeds of information, testing, whatever they've done behind it, and they can be the most benign reading you can ever come across.
Yeah, well, I thought he did some good work, and he presented something which you could say is a dry topic pretty interestingly.
Yeah,
especially with regards to how we were able to break it down.
Absolutely. And this is like he has identified these things that I see all the time. Like maintain cover. Yeah, keep the grass in the ground.
Yeah.
Okay.
Yeah.
You know, if you're going to make supplement, the cheapest supplement you can make is excess grass, like silage or whatever.
Yeah,
That's the cheapest thing you can do. If you're going to do a winter crop, which so many people do in further south you go because it suits the climate and whatever else, prepare. Absolutely prepare and keep the bleeding chemicals out of it. Don't, because we've seen what happens. You saw it with the grass, the regrassing and the maize. There's a direct result of crashing your soil fertility. So keep away from the chemicals. Get smart about it. Maintain the roots. And I'd agree with that, maintain the roots, but I see the big picture is the roots have to be living in a cyanobacteria forest that you can't even see and you're not aware of, okay? And there's some brilliant people out there regarding soil microbe systems and all that sort of thing. And what I can't crazy, they just seem to neglect this part with the cyanobacteria. I don't know why.
Is no one doing a cyanobacteria quantity test?
No, it doesn't appear.
They should do, actually.
Well, as you see, you've seen the video, and we're going to watch it in the next video. You see the little guy eating the cyanobacteria?
Yeah.
Well, that's one of the processes that start this whole soil particulate process going on and the nutritional start and everything like that. So it's so important. You know, support the returns of dung and effort. Absolutely. I mean, I love being a pastoral farmer because they're putting dung on the paddock and it does work. I mean, I move water troughs to places so I can get better pasture covering. You know, when people have gone into this regenerative farming and they go, I move the cows every 3 times, I go, well, I'm not that. I just move them once a day. But I'll go and move a water trough so that I can get better coverage so the animals will shit on a certain part of the paddock. So I will get better production. Because it does affect it. There's no doubt about it.
Okay, look, so any farmers listening to this are going to laugh at me because I consider myself the crash test dummy, the master of no knowledge. Is that because where the water trough is located, you get a lot more poop on the ground?
No, it's so I can maintain that they didn't have to walk very far from that piece, and I can hold them in a particular area and then move them to another area. If the water trough's a mile away, they come over and graze on, then they walk back to the water trough and shit over by the water trough. That's what I mean, because
you got to move the water trough because that's where they're pooping.
Yeah, I want to move it around so I can. Yeah, that's right.
I wasn't so stupid.
We'll give you 5 points.
Thank you, 5 points. Good. Okay, cool. So where were we up to there on that beautiful graphic he's made for us?
Look, brilliant. Photosynthesis. I couldn't agree more, but add in the best photosynthesizer on the planet.
Cyanobacteria.
You just do not go past them. They will stabilize the carbon. Yeah. And we will go to the nutritional benefits of this at the next step because you've got to look at cyanobacteria, a single cell organism. They have every facet in that single cell that we need ourselves. Every facet, every mineral, every process is in there.
You know, it's a funny thought, but if no one's testing for how much cyanobacteria you've got and no one's selling cyanobacteria, then you can only grow what you've got. And you can only have the right soil conditions to improve what you've got. It's not like you can go grab a bag of N and throw it on. You can go grab a bag of cyano and throw it on. So you've got to look after what you've got there to get that most crucial figure of how much activity you've got increasing.
Well, I think the critical thing is if you can find the limiting factors by the soil tests, your behavior, how you're managing your farm and everything, we know how to bring the cyanobacteria to your farm.
In other words, back to life.
We can bring it. We actually have a way of bringing it.
You do?
Yes. And that's bringing the product from the ocean. So you bring sea process back in. Okay, so we'll talk about that on the next video. But
yeah, there's a missing hole in my knowledge there. Thanks.
But it's a beautiful thing. And it's when you really get it to work, it's even more beautiful. And it just becomes so, oh my God, I never knew you could do that. Wow. Look at that.
Yeah.
And it just becomes a lot more fun to farm the whole time.
Yeah. Anything else to say, or is that
No, look, thanks very much, Grasslands. Thanks very much, Louis Schipper. Thanks very much, everybody, for doing the work that, like really points out and has quantified some of the issues that we can say, yeah, we've seen this. We know what's going on here, and we've got to actually stop being so benignly stupid by just going, oh, look, we'll just do this and go and put the spray on. It does a wonderful job. The crop grows brilliantly. And what he's done is shown that the result from the crop, after you've done it that way, has crashed you around.
Yeah, I'm going to just say it for the record, but I think he'd be a really cool guest to have in here. And I hope if he hears this, he might be open to it.
Yeah, that'd be cool. Really cool.
Yeah.